All right, welcome everyone to this week's Autonomy Talk. This week is a pleasure to have with us Professor Bartolomeo Stellato, who is an assistant professor in the Department of Operations Research and Financial Engineering at Princeton University. So some biography of Bartolomeo. Bartolomeo got a Bachelor of Science in Automation Engineering from Polytechnic of Milan, then actually Master of Science in Robotic Systems and Control from ETH Zurich, so it's passed through Zurich at some point in his career. He received then a doctoral degree in engineering science from the University of Oxford and spent some time at MIT as a postdoctoral associate in the Sloan School of Management and Operations Research. You might know him because he's a developer of OSQP, which is a widely used solver in mathematical optimization. And in general, his research focuses on data-driven computational tools for mathematical optimization, and also recently machine learning and optimal control. As you have seen, he has won a number of awards, among which I note the NSF Career Award. Today's talk kind of summarizes some of these research efforts and is titled Learning for Decision-Making Under Uncertainty. This is a very hot topic and very dear to the community of Autonomy Talks, and that's why I'm very excited to hear more about it. So without further ado, Bartolomeo, go ahead. The stage is yours.
Thank you, Gele, for the nice introduction. Thank you for the invitation, and thanks everyone for being here. It's a pleasure. I've been attending remotely and asynchronously on Zoom several of these talks, and it's a great pleasure to connect more directly with a talk of my own with the rest of the community. And today I would like to talk about one area that I'm very interested in lately, which is really modeling uncertain optimization problems. And the hope of this talk is also to try to build more connections with autonomous systems and how uncertain autonomous systems, because I will be presenting several techniques that I think I hope will foster some collaborations and connections with also several of the control community folks. And please interrupt me if you have any questions. I'll keep an eye on the chat as well, and I'd be happy to explain things if they're unclear. So this work is joint work with some great colleagues. So it's primarily led by my graduate student, Irina Wang from Morphy, and then in collaboration with Bart van Parijs, who's a junior faculty at MIT. And then there's also Amit Solomon, who is a research software engineer at Princeton OIT, who's helping us with implementation and software. And then my two senior thesis students, Cole Becker, who's now at MIT, and Annie Liang, who's in Morphy and is finishing her thesis. So autonomous systems, as we all know, they need to make high-stakes decisions all the time. And in the modern world, these high-stakes decisions are becoming more uncertain. So there's several situations in which uncertainty is pervasive, and we need to take that into account when we compute these decisions. So for example, in self-driving taxis, this is actually a video I took myself in Phoenix using one of these Waymo cars. And probably some of you have already used them, but I was for the first time in one of these, and I realized that even if there was construction works or people going in the street, that was pretty reliable how it worked. And I would say the way that, of course, uncertainty is modeled in these kind of applications is can be very different than others in terms of safety. You may care much more about safety in these kind of applications compared to other applications where you're allowed to violate constraints, but still it's a very challenging problem to make it work. And I think there's still lots to do to make it work, not in the streets of Phoenix, but for example, in Italy. So there's other situations, for example, that are where uncertainty is important, like energy grids. There's always problems where we need to decide how to dispatch the energy in the grid. And there's two main sources of uncertainty that are the loads, so the demand in the grid, and also the power generation from renewable energy sources that are much harder to predict compared to traditional non-renewable energy sources. So we need to take that into account where we solve energy dispatch or unit commitment problems. Also in finance, there's the typical problems that actually some of them we will see them today are about really portfolio optimization and allocating assets. And the main problem is affected by uncertainty because we don't know future returns. So we need to estimate them and reason in a way that takes into account future returns. And another problem that, of course, I'm very interested in that is affected by uncertainty is robotics, where the decisions need to be made even more quickly compared to, for example, a problem in the energy grid where you need to solve the problem every 15 minutes. In robotics, you have a few milliseconds to do it, and there's several sources of uncertainty. You might have obstacles that move around, humans that are interacting with the robots, so you need to take that into account. And one of the most powerful tools that we have to do that is through real-time optimization. In particular, real-time optimization is this way to deal with autonomous systems where every time you compute the actions, you solve an optimization problem where some data and some parameters enter, and that could be, for example, the state of your dynamical system or the positions of the obstacles or the target that you want to reach. And then you solve an optimization problem where you compute your decisions, and your goal is to minimize a certain objective that could be the energy consumption, the cost, a distance to the target. And then the constraints are your dynamics, physical limitations, or if you're in a portfolio allocation problem, your budget constraints. So this real-time optimization framework is very common in autonomous systems, also referred to as, in many situations, as model predictive control. And it has several benefits. And I would say the most remarkable benefit is that it's really the fact that you replan every time you resolve an optimization problem and you recompute your plan of actions allows the autonomous system to become more resilient and adaptive. So the merely fact that you're resolving these problems all the time really gives an intrinsic, through the feedback loop, giving an intrinsic resiliency to the system. However, it's not always easy to solve optimization problems in real time. In particular, there's two main challenges that I think need to be taken into account. So the first one is computational speed. So you need to solve these problems in real time. And real time doesn't mean necessarily super fast, but it means you need to have very strict computational limits. And sometimes they're hardware limits, so the processors are not very powerful, the ones where you solve the optimization problems on, but also you don't have that much computational time. So if you have a problem, for example, mechanical system, usually you need to react every few tens of milliseconds. Another issue is that the kind of uncertainty that we're dealing with right now is much more pervasive than what we were used to in the past in all these interactive scenarios that I talked about before. So we need to take into account uncertainty when we formulate the optimization problems. We cannot give up uncertainty and just hope that the feedback loop takes care of everything. But the opportunity to deal with these challenges is that several of these problems that we deal with are very similar to each other. They're actually the same optimization problem that we solve over and over again. And the only thing that changes are the parameters y, which are the data that enters in the problem. For example, the dynamics of your autonomous system is not going to change every time you resolve this problem over and over again. What changes is probably the state of your dynamical system. Or in an energy grid, the layout of the grid is not going to change every time you resolve this problem. What changes is the status of the batteries in your grid, and also the loads that you want to satisfy, or the forecast for the wind energy produced. So these problems are all similar to each other, and the mere fact that we're solving them over and over again generates a lot of data that we have to that we can use to address these challenges. So in my research and my group, we use these data to learn to solve this problem better, to build better decision-making tools using learning. So we try in my group to combine theories of optimization, learning, and control, and build methodologies that address these two challenges. So on the one hand, optimization under uncertainty, and on the other hand, which is something that I've been working intensely, and I'm still working intensively on, which is real-time optimization algorithms. And the idea of these methodologies is to connect theory to several applications where you need to solve these problems in real time and take into account uncertainty, for example, autonomous system, urban mobility, but also finance and power systems. So within the spectrum of areas and methodologies that I'm interested in, what I would like to talk about primarily today is optimization under uncertainty, how to formulate these problems, and how to use data wisely, and how to keep the problem formulation tractable, especially if you then want to solve them in real time. Okay, so now let's focus on optimization under uncertainty now, given that we have the setup, and in particular, how to model these problems when we have uncertain objectives or constraints. So now, what's the framework that I will describe in this first, at the beginning of the talk, would be a simple problem where you want to minimize a certain objective of your optimization variable x, and you have an uncertain parameter u that enters in the constraint. So you would like to satisfy your constraints, and you want to compute solutions that satisfy the constraints before you actually see the realization of the uncertainty. Okay, so this is, as it's written like this now, is not a very well-defined problem. So we need to adapt it in order to ensure that the constraints are satisfied if this uncertain parameter appears after we commit to some decisions. So one approach that is extremely common in the literature is to use robust optimization. Robust optimization is very intuitive, is very expressive, and it's been used in several different areas, including from operational research, but also robust control, and also in machine learning applications, it's very popular to use robust optimization, which is just works as follows. You pick an uncertainty set, and then you ensure that the constraints are satisfied for any realization of the uncertainty inside this set. Okay, and this can be this constraint that you obtain now, instead of being the one from the previous slide, is for every u that lives in this set. That's it's a constraint that, if you look at it, is actually infinite dimensional, because you have an infinite number of u's that lives in this set, for example, if it's a convex set. However, there's several constraints that we can reformulate in a tractable way and remove this for all u. So there's, for several constraints g that are, for example, concavity uncertainty, and this set that is convex, you can always reformulate it very easily. And this is independently from the decision variables. Decision variables could be also discrete here. Okay, so that's not there's not a problem for this. So now sorry, I'm just trying to up 1 second. Okay. So the PKD uncertainty sets, however, it's not very easy, in the sense that it's the main crux of robust optimization. So we cannot really, it's hard to define this uncertainty set. So how do we build that? Because that's the hard part. Formulating and solving the problem is actually easy, but how do we build the uncertainty set? There's several ways. A simple approach one might think of is the worst case approach. For example, if you know that your uncertainty is never negative, for example, the load demand on a grid, you may build the uncertainty set to be the entire support of your uncertainty. Now, this is very conservative because we don't use any information besides the support. So if you know the probability distribution of the uncertainty, you could build an uncertainty set that covers a high amount of the probability mass in order to make these decisions. And this is very common in several theoretical works in optimization and robust optimization. However, it is not really it's not very practical, in the sense that nobody knows the true distribution of the uncertainty. And even if you know it, unless it's Gaussian or very specific, it's hard to formulate the constraints tractably. More recent approaches, however, try to use data to construct these uncertainty sets. And using data is everything that we have, unfortunately, in these scenarios. We have previous realizations of the uncertainty or realizations of the problem that we want to solve. So what I would like to focus on in this talk is really to use data to build this uncertainty set to have solutions that satisfy the constraints with high probability. And in particular, I would try to answer this question, in which I would like to build uncertainty set that give me tractable problems, and also such that the solutions that we obtain have high performance, in the sense that they're not conservative. And I will focus on two main machine learning techniques. I will focus on the one hand on clustering procedures, where you're, instead of selecting all the data, you try to compress data and look at the cluster means, the cluster centers, instead of the original data. And on the second part of the talk, I will look into differentiable optimization, which is using and modeling the optimization, the robust optimization problem as a layer of a computational architecture such that we can train the parameters of the uncertainty set while satisfying the probabilistic guarantees. So let's focus on the first part on the clustering procedure. So clustering is a very common approach in machine learning. It has been studied for a very long time, and there's several very, very scalable algorithms to solve clustering problems. And I'll show you how we could use it to actually build more computationally savvy formulations. But before jumping there, I would like to mention which kind of probabilistic guarantees we would like to enforce. So the finite sample guarantees that we would like to enforce are defined as follows. So for simplicity, I will model the fact that the expectation of my constraint needs to be less than or equal to 0. Okay, so that's our G constraint. I would like the expectation to be less than or equal to 0. This is for simplicity, however. In the paper, we actually have extensive representations of the constraints in terms of also the probability that this constraint is less than 0 is very high. But for simplicity here, I will just use the expectation. And as I said before, we don't know the distribution of U. So this probability distribution, we don't know it, but everything that we have is data. So I would like to use n data points to actually formulate an optimization problem that after I solve it, I obtain a solution Xn that has this data-driven probabilistic guarantees. And what is this kind of guarantee? This is the probability, the product distribution over n draws of these samples di. And for every draw, I would like to get some samples that give me this data-driven solution X at n. And this solution has to satisfy the constraint in expectation with high probability. Okay, these are very common probabilistic guarantees that we would like to ensure often in practical applications. And this is common whenever you want a finite sample probabilistic guarantee, because you just have a finite set of data and you want to build solutions, the green part, that satisfy the constraints with high probability over the draws of n samples that we may get from the true distribution that we cannot know exactly. So now, how can we do that? How can we construct this solution X out of n? The most common thing to do after you have some data is to associate the empirical distribution to the data. So if you have n data points in this plane, what you can do, the most intuitive thing to do is to assign an empirical distribution p hat of n that assign equal the probability of obtaining one of these samples is equal between each of the points. And what we can obtain from this distribution, because it's not going to be exactly the true one, we can build a commonly referred to ambiguity set of distributions, where we consider the empirical distribution as the center, and then we refer to all distributions P that are not too far from the empirical one with respect to this Wasserstein distance. Okay, this is a very common metric that appeared recently from several seminar works by Kuhn, Esfahani, and several other co-authors at ETH, actually, including Florian, Soroush, and also Wolfram as well. So there's several authors that started to work on this area recently. And the nice thing is that it has beautiful connections with optimal transport in terms of defining the distance between these two distributions. But I'm not going to define it as you can normally see it in several talks. I would like to just mention here that is the distance between the empirical distribution and the true one, and I would like it to be less than epsilon. So distributionally robust optimization with the Wasserstein metric does this. So formulates the problem and assumes that the true distribution is inside this ball. And this is there's several ways to derive surprisingly tractable formulations for this. However, there's some disadvantages that I would like to mention from these kind of approaches, which are the computational costs. So comparing robust, which is the typical problem where you just have one uncertainty set that could be an ellipsoid where the uncertainty lives, and this distributionally robust optimization, specifically with the Wasserstein metric, if you compare them on two axes in terms of conservatism and computational effort, then I see that the robust optimization approach lives here, where the computational effort is very low compared to other approaches because you have one constraint and you reformulate it with another constraint that is usually not very high dimensional. For example, if you have an ellipsoidal set. The distribution robust optimization lives more in this area, where by using the true data points to formulate this set, he can be much less conservative because you really model closely the set using data. However, the computational effort is very high, and I'll show you why this is the case. Because to model one uncertain constraint, you need to replicate it linearly in the number of samples. So to formulate one constraint, if you have 10,000 samples, you get 10,000 constraints. And if you have a problem with discrete variables, it's going to take a very long time to solve it. What I would like to focus in this first part of the talk is actually something in between these two approaches, where we can combine conservatism and distributionally, reduce the conservatism of robust optimization and the computational effort of distributionally robust optimization.
Bartolomeo?
Yes?
There is a question in the chat from Subrata, and I thought it was good to get rid of it right now. So there is two questions. Is it true that the better the clustering, the closer to the worst case value? And also, what is the advantage of designing a linear constraint?
So these are two very interesting questions, and I will address them. Actually, they will become more clear, the answers, in the next slides. So we will actually quantify exactly the effect of clustering and the effect of conservatism after you cluster. And also the advantage of designing a linear constraint is that you will get a much faster problem to solve. And I'll show you that you can get several orders of magnitude speedups by using clustering before. Unfortunately, now I haven't explained everything, but I will address both of these in the next slides. But these are great questions. These are actually some of the questions we try to actively answer in this paper. Okay, so now what does clustering do? That's a very interesting approach that just assigns a bunch of data points to classes, in this case, 3 classes with the green, orange, and blue points, and then tries to build in order to do that, you need to solve an optimization problem to cluster the points. And the optimization problem is the problem of minimizing the distance between every point and the assigned cluster center. Okay. So for every point that belongs to the assigned points to the cluster K, which is CK, and we want to minimize the distance between that point and the cluster center, and we sum the distance across every cluster. And then we get the objective that we solve in the clustering problem. This problem is NP hard, it's hard to solve, but we have excellent methods that are super scalable. They give you pretty good solution. We don't want to find the global optimal for this problem. We're happy with a good clustering solution. And so, for example, one of the approaches is k-means clustering. This scales to very large dimensions, and it gives pretty accurate answers. There's also several recent works on using mixed integer optimization to cluster the data points. We don't need that for this framework. Actually, you could use your favorite clustering routine, and we will work with what the clustering method gives us. So the main idea is to actually use the cluster centers instead of the original data. And it is something that goes more deeply in how computing and data is evolving. So if you think about computing is, for example, with Moore's law basically ending, we're not really increasing exponentially the speed of our processors every year. But the amount of data that we have available is growing exponentially every year. So these two kind of conflicting trends really push us to think about ways to model the uncertainty that are more data savvy. And clustering is a very simple idea to go in this direction. So how does our method work in this area? So our method, we call it mean robust optimization. And it works as follows. You get a set of data points, and then you generate an uncertainty set that depends on capital K, which is the total number of clusters, and the radius that is set. And after you get this uncertainty set, we solve this mean robust optimization problem, which is a similar problem than what we had before. But we have this uncertainty set that appears here, and the constraint function that appears here, which is there's slightly different than what you had before. This uncertainty set in blue, it's slightly different than what we've seen before. And the constraint function is G bar, is not exactly G, which is the constraint that you've seen. So now I would like to connect and walk you through the uncertainty set and the constraint function from how we define it in this framework. But at the end of the day, this is going to be a robust optimization problem that uses the cluster data to define the uncertainty set. So how does this framework work? Let's look at the uncertainty set first. The uncertainty set is given by this formula, which is a lifting of the uncertain parameter. Instead of having the original dimensions, we lift it into capital K times the original dimensions. Okay, so instead of having the original uncertain parameter, we have V1 to Vk, which are the uncertain parameters that represent our uncertainty set. And then we constrain them in this way inside the uncertainty set. So we sum over all the clusters, K1 to capital K, the cluster weights Wk, which is the proportion of samples assigned to the cluster using your favorite clustering procedure. And then we multiply it by the distance between Vk, which is each one of these parameters, minus d bar k, which are the cluster centers that your clustering procedure gave us. This distance is measured in your favorite norm. For example, 1 norm, 2 norm, infinity norm, it's not important. And then each one of these norms is raised to the power of p. Okay, this order will be a little bit more clear later, but it's also a tuning parameter. This could be, if it's 1, you just look at the norm. If it's 2, you raise this to the power of 2. And this set is very generic, and it can describe several sets that we actually know. So to make it more clear, I'll show you now what happens if you vary the number of clusters and also the order of the set. So let's say that now I have an axis where I change the number of clusters, and I go to the extreme case. So this is k equal to 1. I have 1 cluster. What am I doing? I'm just computing the mean of all my samples, and I take the mean, which is d bar 1. I have 1 cluster, and I construct a ball around the mean of the sample. This is a typical set in robust optimization. It's the typical ellipsoidal set in robust optimization, okay, which is very simple. Now, what if you have 3 clusters, and let's say that p is equal to infinity? If p is equal to infinity, this summation actually breaks and becomes a maximum. And once you get the maximum between all the components, you're actually getting individual norm balls centered at the mean of each one of these samples. Okay, for example, d bar 1 is the mean of 1 cluster, 2nd cluster, and 3rd cluster. And we have each one of these perturbations is inside these balls that are disjoint with each other, each one with radius epsilon. Now, what happens if you have k equal to n, so you're not clustering anything? If you don't cluster anything, and let's say that p is equal to 2 and you have the 2 norm, what happens is that you have a very high dimensional ball that is centered at a point that is constructed by stacking together all your data points. And the radius of this ball is epsilon times the square root of n. Okay, so this set is actually an exact representation of the set that you obtain in Wasserstein distributionally robust optimization. This is exactly what you obtain there when your clustering procedure does nothing. Okay, so these are different sets, and you can construct different, also more sophisticated sets by varying the parameters or the number of clusters. But this set is very important because then if you plug it into the problem, after you lift the uncertain parameter in these dimensions, and you obtain this set from the previous slide, then the only thing that is left is now to define this constraint function as this weighted mean over the original constraint function G, where every component is weighted by Wk, which is the proportion of the samples assigned to that cluster, where Vk is the perturbation that corresponds to one of the elements inside this vector U. So this is a robust optimization problem, and you're taking the weighted mean for the perturbations in the uncertainty set and for the constraint itself. And the interesting thing is that after you have a robust optimization problem, you can actually formulate it and solve it quite easily. So the typical way to formulate it is to dualize the constraints. So to take the, instead of having an uncertain, this constraint for every u that lives in the set, you take the supremum over the u's that live in the set, and then dualize it with a couple of tricks for convex duality. And what you obtain is a problem that looks like this. So this problem, you just sum all the weights, the cluster weights times sk, and then sk upper bounds these quantities. Now, this seems a little bit complicated, but actually it's all based on things we can easily compute. For example, we have the conjugate function of minus g, which is very easy to compute if you have a concave function with respect to the uncertain parameter. These are the cluster centers that we talked about before. And this is phi of p is a function of your power, which is if p is equal to 1, this is 0, or it tends to 1 as p equal to infinity. But it's not very important for you to understand this part. I would say the interesting thing about this problem is that if you ignore the details inside here, is actually that to reformulate one scalar constraint, you have capital K constraints, where capital K is the number of samples. So the fact that you use a data-driven formulation for this problem leads to a very large number of samples that may lead to a very complicated problem to solve if you have, let's say, several of these constraints to dualize. So if K is large, you have a large number of constraints, but we can decrease capital K depending on how we cluster the points. And actually, the interesting thing about these formulations is that by varying the number of clusters, we can go between a robust optimization problem where we have just one cluster and one ball around the mean of the samples to the distributionally robust optimization problems with the Wasserstein metric that many people in this audience are familiar with. So in other words, the number of clusters allow you to trade off computational complexity and conservatism. So I haven't talked about conservatism yet, but that's also an important thing that was actually related to one of the questions about what's the worst case value. So which probabilistic guarantees can we still ensure after we cluster the points? So what probabilistic guarantees do we get if we don't cluster the points? That's a very, let's go back to the finite sample guarantee that we talked about before. If you have a probability of constraint satisfaction of y minus beta, then it's well known that if you take some easy assumptions, for example, light tail distributions, you can construct a radius epsilon that depends on the number of samples and beta and some other coefficients from the distribution. But I would say from the number of samples and beta, we can construct a radius epsilon that gives you a solution x(n) that satisfies these probabilistic guarantees. Okay, so this is not our result. There's several results that use this approach, and it's quite direct, the computation, and it works very elegantly. However, if you cluster the points, you don't have this direct radius. So how do we adjust the radius? Our contribution is that we looked at how to adjust the radius, and the easy thing to ensure the same probability of constraint satisfaction is to actually add something to the old radius. And what do we add? We add something that depends on how well we cluster. This expression in green is the sum of the distances between every point in the cluster centers raised to the power of p. So this means that the better we cluster, then the less we need to increase the radius to have the same probabilistic guarantees, which is exactly close to the first question that was asked in terms of, does better clustering help us in terms of the worst case value? And the answer is yes. So you can choose your favorite clustering procedure, but then depending on how well you cluster, you need to adjust the radius accordingly. Now, this is all beautiful in theory, and this works well in a paper. However, if any one of you has worked in actually implementing these things, you know that these bounds are extremely conservative. Okay, so it's very hard to, because they just assume very little about the distribution. So we wanted to bound the conservatism in a more direct way. So what we did is that we looked at the worst case value of the constraints after we have n points or capital K points. Okay, so let's define the worst case value, which is the maximum or the supremum over U in this compact set with n samples, and the one with capital K samples. And I want to understand the relationship between these two worst case values. So in a very simplified way, so depending on the curvature of minus g with respect to u, so if minus g is L smooth in u, we have this very nice relationship between the worst case value of the constraints, g bar n, and g bar n of x plus this quantity here. So these two components sandwich together the value once you have k clusters. And what is this component here? This component is L divided by 2, which is the Lipschitz, the L smooth constant of minus g, and dk is exactly the clustering objective. So it's literally the distance between the cluster, the points and the cluster centers to the power of 2, which is the typical clustering objective, for example, in k-means clustering. So what does this result tell us? This result tells us that the better we cluster, the less we need to increase the worst case value of the constraint, which means that the solution will be less, we introduce less conservatism. For example, if we have just 3 points, a distribution that has just 3 Dirac's at the cluster means, then clustering is perfect in this case. So this is 0, and then we don't introduce any conservatism. However, we may have conservatism introduced by clustering or by the fact that a small number of clusters cannot capture the entire distribution. But the interesting thing on top of this part is that L plays an important role. So G is affine in the uncertainty. L is equal to 0, which means the clustering makes no difference in the optimal value or the optimal solution, which means that if you have a linear function of U and you're using distribution robust optimization, Wasserstein distribution robust optimization, you should just cluster all the points together and get one cluster and get one uncertainty set using robust optimization. There's no need to have higher than 1 clusters in that case. Now, this works for functions that are concave in U, but in the paper, we have also generalization to maximum of concave functions in U. That I don't want to dive into too many of those details, but instead of going there, I would like to show an example of how much computational time this can save us. So this is probably more common in OR, but it's just to give you an idea of what happens for a discrete optimization problem. So this is a typical capital budgeting example where you have n projects and you need to decide which one of these 10 projects to start. Okay, it could be also a resource allocation problem that you want to where you want to allocate these resources. So, and then you need to decide whether or not to assign these components of x. So this is a binary variable, and you have this component here, which is the net present value given these decisions x. This is a linear function of x, but it's a concave function of u, and I'll explain you why in a second. And then you have a budget constraint that tells you that you cannot allocate all the projects, for example. And the net present value of a certain project, just remind you, just the sum of the over a certain horizon. So this is a multi-stage problem where at every time step t, you want to sum the discounted cash flows. The cash flow is known, and then the discount rate is the uncertainty that appears. So this is a nice example of a concave function of the uncertainty, because if you have a linear function of the uncertainty, you just, the k equal to 1 works all the time. So we chose a concave one. And I wanted to show you what happens here. So these are the bounds that we obtain. And these are the this is the difference between once you have k cluster and when we have 0 cluster. Okay, when we have n clusters, sorry. And this is how the number of clusters on the x-axis changes. This is also with the number of clusters changing. And these are the bounds from that we derive with the worst case properties, and these are the true values, and this for vary epsilon, which is the radius of the uncertainty set. And now on the right, I described the computational time to solve this problem. So you could see that if you have 100, this is for 10 projects in a horizon of 50. So this is not a huge problem. However, it's a binary problem. So if you want to solve it for 120 data points, which is not that much, but it still gives you a problem that takes 100 seconds to solve. So forget about solving it in real time if you need to do it in applications where you need to solve it in milliseconds. But if you cluster, then if you have, let's say, 1 or 2 clusters, then you could actually solve it in about a second or less, which is very, very important for real-time applications. And what happens about the performance, interestingly, at least in this example, not in every example, but in this example, we compare the autosample probability of constraint violation and the autosample average objective value. When you have k equal to 1 cluster, and this is the blue line that stops here. So no matter how you change the radius of the uncertainty set, you can't get an objective that is below this quantity. But with 2 classes, we get the orange line, which allows you to get a lower objective. And with 60 clusters or 120 classes, you get the entire Pareto frontier. But the interesting thing is that with just 2 classes, which takes a very little time to solve, you get near optimal performance. And in many situations, this happens because the distribution may have maybe 2 or 3 classes, and you don't need a huge amount of classes to deal with uncertainty. So let me just wrap up this part. So this mean robust optimization framework allows us to bridge robust and distributional robust optimization by varying the number of clusters that we have before formulating the optimization problem. Quantify the clustering effect. If the function is affine in U, we have 0 clustering effect. If G is concave in U, we derive the performance bound. Actually, in the paper, we have maximum of concave in U as well. And we have multiple orders of magnitude speedups because we're simply solving a smaller problem. So this is very helpful in several applications. So this is the code to, if you want to reproduce this result, there's a paper on arXiv. And if you want, there's also the QR code. And this part, I would say, can build lots of stronger connections with I believe, the control community. This was more from the optimization perspective, but I think especially for people interested in real-time computation, there's lots that can be done by combining clustering and optimization under uncertainty. So now, before jumping into the second part, I wanted to ask, are there any questions from the people who are attending? Okay, so if not, let's jump to the second part, which is how to use differentiable optimization to build better uncertainty sets. So now, what is differentiable optimization? Is this way to use optimization problems in an architecture that allow you to, by computing the sensitivities of these problems, to adjust the parameters of these optimization problems in a similar way as we train a neural network. And I would like to give you a motivating example of why the shape of this uncertainty set matters a lot. This, again, similar portfolio optimization problem that we had before. So now I would like to minimize the negative returns. So it's minus U, which is the uncertain returns. Now I keep it 2-dimensional to actually visualize what's going on. And I would like to minimize minus the uncertain returns, which means I want to maximize the returns. And then I want to add one norm penalty that penalizes my decision, the distance between my decisions and the previous holdings. So this could be a difference between how much we are actually penalizing how much we trade. These are trade costs. There's actually an interesting monograph by the group of Stephen Boyd, where they describe several approaches related to model predictive control to solve these problems. And interestingly, the previous holdings is part of the information or the state information that we carry around. Okay, so that's important. Every time we need to solve a trade allocation problem, we need to take into account how different our allocations are compared to the previous allocation. So, and this lambda is how much we weigh this difference. Okay, so that's a simple problem, an XRR investment decision. So it can be written as a robust optimization problem where we add a variable t, and we have this uncertain constraint that t is greater than the negative returns for every realization of the uncertainty inside this set. And then have the typical constraint that says that the sum of these allocations needs to be 1 and x to be greater than or equal to 0. So now, how do we pick the uncertainty set in order to perform well for returns that we haven't seen already? Okay. So let's look at the performance of 2 different sets. So one is a mean variance set, which is the most typical set you could think of. Let's say that you have set parameters theta that define how my uncertainty is. And the mean variance set is the typical ellipsoidal set, which I will call MV of theta, where U is given by mu, which is the mean of the uncertainty, plus sigma square root that multiplies Z. And Z is this parameter whose norm is less than rho. This is very common in robust optimization. This describes an ellipsoid. Okay, and this set can be described as this vector B and matrix A that define the parameters of the set. How do we compute this parameter? We just compute the empirical mean and covariance of this set. of these uncertain realizations that we have. Now, let's say that I have another set that is very similar, but is reshaped, and B and A are different and don't even cover most of the samples that we're taking into account. Let's say that this is a completely different set, and I would like to understand the performance of the typical mean variance set and a reshaped set as we change the radius of this set. And let's look at what happens here, and especially, can the reshaped set do better? Now, keep in mind, before showing you the plot, I would like to mention that this problem is solved for realizations, is a parametric problem where every time you solve it, you change this parameter here, okay? So we assume that this comes from a Dirichlet distribution. Dirichlet distribution is just because we want to ensure that the sum of the elements of X is equal to 1. And I have samples of these, samples of U, and I would like to get the performance of these two uncertainty sets, or of these two uncertainty sets, the mean variance and the reshaped one, for different samples. So what happens here is that I try to change rho, which is the radius of this uncertainty set, and I have the auto-sample probability of constraint violation and the auto-sample objective value. I have the mean variance set, the performance, and the reshaped set here below. So you can see that the reshaped set can do much better for this example. And let's look at the kind of set that we have here, because it's a two-dimensional problem, so we can actually visualize it. So the mean variance set, if you want the auto-sample probability of constraint violation equal to 0, it kind of covers all the data points, okay? Now, if we want to violate a little bit the constraints, we cover them a bit less and a bit less here. Now, the reshaped set, if you want 0 violation, doesn't even cover much of these samples. Actually, there's a lot of samples that are outside the set, but the probability of constraint violation is very low. And this is even for a smaller set, and even this set covers a very small amount of data points. Okay, so how can we find such set that is reshaped, and also why are we actually ignoring the fact that lots of data points are outside this set? So there's actually a very nice quote from the robust optimization book by Bentale, Mirovsky, and Gaui, where at one of the first chapters they talk about the immunization power, which is the probability of constraint violation, and the fact that it cannot be explained by the fact that the underlying perturbations set, they call it perturbation set, contains nearly all realization of the perturbation vector. So actually there's lots of sets that we can construct that contain no points. Actually, they have an example in one of the first chapters where they have a set that contains no uncertain realizations, but has very good probability of constraint satisfaction. So how can we deal with that? We need to give up the fact that we need to cover a high probability mass. And instead, we need to think a little bit about it differently. So let's compare how some data-driven methods for robust optimization build these uncertainty sets. So this era started more than 10 years ago with several techniques from hypothesis testing, quantile estimation, but also Wasserstein distributionally robust optimization based on the first part of the talk is a way to construct a robust uncertainty set. And also deep learning more recently, there's different ways to actually use neural networks to predict the uncertainty sets. And all these approaches, while very powerful, they rely on a very important thing, which is the high coverage requirements, which means that you always build an uncertainty set that contains a high amount of probability mass, independently from the rest of the optimization problem that you're solving. So actually, you don't look at the solution that you get before adjusting the uncertainty set. You just construct the set before, and then this set will be more conservative than necessary because it will work for any problem where you plug the set into, which is not exactly what we need in some applications. So instead of looking at this characteristics of covering a high amount of probability mass, we will give up high coverage requirements, which is this property here, and we will build a architecture that exploits the solutions of your robust optimization problem. So we will solve optimization problems that are parametric in Y, which is the parameter that I described at the very beginning of the talk, which could represent a state of the dynamical system or a context parameter that define whatever you know at this point. And then you plug it into your constraints and the objective, and then this problem will give you a parametric solution that then we will judge with a loss, and we will use this loss to adjust the parameters of the uncertainty set. So the main idea is to actually use differentiable optimization to automatically learn the shape and the size of this uncertainty set by judging the quality of the solution that we get after solving this problem. So let's maybe boil down, let's describe more in detail the actual problem that we solved, the robust optimization problem. So this is the problem that we're interested in detail here. So we want to model a parametric robust optimization problem that depends on your parameter y and the uncertainty set parameter theta. And you compute these decisions x here. You have an uncertain parameter u that we want to deal with. And you have this family context parameter x that enters, in this case, just in the constraint. You can always write this parametric problem such that this affects only the constraints. For example, in a predictive control problem, this could be the right-hand side of your linear constraint. It's affected by the state of your dynamical system. So this enters always the constraints. And u is also affecting the constraint. But the difference between y and u is that y, you know it before you compute x. U, you don't know it, okay? So there's a difference between these two kind of parameters that enter. But what we would like to build is probabilistic guarantees that hold over distributions of u and y. Okay, so we want that my solution x theta y, which is after we solve this robust problem, if we plug it into the constraint and we take the probability over u and y, this constraint is satisfied with a high enough probability. So that's the setup. So we want to solve a robust optimization problem, choose the parameters of the set such that we have these probabilistic guarantees that are satisfied. So how do we construct a set that ensures these probabilistic guarantees? So to do that, we need to take a step back and think about how to enforce these guarantees in a tractable way. This probabilistic guarantee is actually a not so easy object to deal with. And in particular, having a probabilistic guarantee of this kind is the same as having a value at risk of the g of g, which is your constraint, value at risk parameterized by eta, which is the target probability of constraints violation. This value at risk needs to be less than or equal to 0. Okay, because this is the upper bound, the minimum upper bound to the value of your g function. That's a very hard object to deal with. So as you work with some of these objects, is not an easy thing to model, especially if you want to use it inside a training procedure. So instead of doing that, we build a tractable approximation, which is an upper bound to the value at risk, which is a conditional value at risk. This is very well known in risk measures, but also in control. And the conditional value at risk has very nice properties, including the fact that it is the expectation over this tail that is above the actual value at risk. And the nice thing of the conditional value at risk is that there is nothing else than an expectation constraint for your problem. So in other words, the conditional value at risk can be modeled as a constraint that is an expectation constraint that depends on your constraint g minus alpha, which is an additional parameter. And this plus takes the maximum between the argument here and 0. So in a way that we use to tune the set, we will enforce this expectation constraint such that this is less than kappa. Now, it should be less than 0, but we will say less than kappa, which is a slightly negative value, in order to enforce auto-sample probabilistic guarantee, finite sample probabilistic guarantees for unseen future data. So that's a constraint that we need to enforce while we choose theta, which are the parameters of the uncertainty set. So now, how do we tune the uncertainty set? We need to solve an optimization problem to tune that. And in particular, this is a stochastic bi-level optimization problem that we need to solve. Why is it stochastic? Because we want to minimize the objective, which is the expectation over y, where y are the context or the parameters that affect my robust optimization problem. And the expectation of u and y is in the constraint that models the CVAR constraint that I told you about before. So this is a stochastic problem. And it's also a bi-level problem because this x depends on the solution of the robust optimization problem that we're modeling here. Okay, so now there was a question about, can the CVAR be 0? And its implication, actually, the CVAR can be 0 And what we care about is actually the CVAR to be less than or equal than 0. Okay, so if the CVAR is 0, it means that there's an upper bound to the value at risk that is also is definitely less than 0, which means that if the value at risk is less than 0, it means that the probability of that the constraint value is less than 0 is definitely higher than 1 minus zeta. So this is exactly what we want if the CVAR is 0. Okay, and we want to enforce it inside a constraint of our training problem. Okay, in this case we say kappa, which is slightly less than 0, but that's the kind of problem that we use for training. And we have an inner robust problem that is underneath that we need to solve. This problem we will actually compare to the first part of the talk. This problem does not have integer values. It's a convex optimization problem. The inner problem here. The outer problem is not going to be convex. It's not going to be smooth. It's actually a nasty problem. Okay, that I'll show you how we actually solve it. So how do we go about solving this problem? We first need to formulate this inner robust optimization problem and remove this for all constraint and see where the parameters enter. So let me show you a quick example of how the uncertainty set parameters enter in the formulation. So let's say that I want to see where these parameters enter theta. Now, and I have an ellipsoidal set that is similar to what we had before. And now theta is actually A and B. So it's this matrix that multiplies Z, and B is a vector that is added to the product, and this gives my uncertain parameter U. So for example, if you have a linear constraint that depends on Y, which is our convex, plus PU, and then let's say that this product with X has to be less than or equal to 0 for every U that lives in this set, you can reformulate it using these parameters B and A, and B and A will appear here. Okay, so for many sets, these parameters enter linearly in the problem. And in particular, it entered in a way that is very well structured that we can play with for our training procedure. So there's several examples in the paper on more of these parameters. But what I would like to mention briefly, I'm not going to go into too many details, but I would like to mention how we actually solve this problem. So we solve it using a stochastic augmented Lagrangian algorithm. So if you define the objective as capital F of theta, and the constraint as H of theta, alpha and theta. Alpha is the additional variable that we need to introduce to model the CVAR. Then we can build an augmented Lagrangian algorithm where we have this multiplier lambda and the penalty parameter mu that we use for the augmented Lagrangian algorithm will adjust the multiplier and the penalty parameter in order to get to a solution that satisfies the constraints. And the main important thing inside this augmented Lagrangian is that the stochastic gradient computation, which is the estimated gradient of the Lagrangian with respect to theta, which is actually a Jacobian, is not precisely a gradient. It depends on the Jacobian of X with respect to theta. So what is this object? This object describes how X changes if you change the parameters theta. And this comes from solving this inner robust optimization problem. And to obtain this Jacobian, there's several interesting works lately that differentiate through the KKT optimality conditions of the inner problem. And the nice thing is that you can use interesting packages that, for example, CVX layers that allow you to, if you formulate a robust optimization problem, to actually plug it into this augmented Lagrangian procedure and solve this training problem offline. This problem is nasty, but it's solved offline. So you can think about it as a training procedure that you can perform with more time available compared to real-time computations. So the convergence analysis, very informally and briefly, the main idea that the main thing that we constructed for this convergence analysis is that we use this path differentiability of the solution X with respect to theta and Y, and also by consequence of the actual augmented Lagrangian function. And this happens if the inner robust problem is convex and conic representable and has a unique solution. And it's always possible to construct a problem that has a unique solution unless, and you can always regularize it in many cases. For example, in control problems, you can always write it as a strictly convex problem, which implies this. Now, if you have path differentiability, means that chain rule works. You don't have edge cases that break. And also you can improve that if the sequence of penalty parameters is bounded, then the algorithm converges almost surely to a feasible point theta star for the training problem, which means a point that gives you a solution that satisfies the sample constraints. Okay. Now, it doesn't always converge. So you may have situations where you get the penalty parameters that are unbounded. In this case, you don't get to a feasible point. And this is absolutely normal because we're solving a non-convex problem with an augmented Lagrangian algorithm. So it depends on the initialization. The thing is that you should look at this training procedure as something that is done also for neural networks, where there's some tuning to be done offline to actually get the right augmented Lagrangian steps and to get the right stationary point. But this works and you get to a feasible point. It will not be the globally optimal, but we don't care about the globally optimal. We want a solution that works well, for which we can verify that the constraints over your training data are satisfied. Now, I haven't talked about auto-sample guarantees, but actually we want to understand what happens for unseen data. And the main trick to deal with unseen data is actually to tune this threshold parameter in your CVAR constraint. So this threshold parameter is a parameter that we can formulate based on the optimality tolerance for the training problem, the target confidence that we have, the dimension of X, and the number of samples of U. If we choose it accordingly, I'm not going to write the exact expression, but this parameter, if you enforce then the CVAR constraint in your training problem to be less than kappa, then we can show that this implies finite sample probabilistic guarantees using tail bounds and the fact that CVAR is a tail concentration bounds and the fact that the CVAR, the conditional value at risk, is above the value at risk. So we can get a finite sample probabilistic guarantee for any X that lives in the possible set of solutions that we may obtain for our parametric problem. And this is over draws of N samples of U and J samples of Y. Okay. Interestingly, if it holds in this way for every X that lives in this set, it holds also for our X that comes after solving the inner robust problem. These are more theoretical result. I would say in practice, these concentration bounds are very loose in a similar way as these Wasserstein results with the tail bounds also are conservative, but it's good to have a knob that we can tune that actually give us exactly the probabilistic guarantees. So now let me talk briefly about the code, an example, and then I think we should be we can wrap up. So the code that we're actually building, we would like to actually build something that is reusable in the future. It's not easy, but the main idea is that we would like to define these problems using a framework so that it's easy to dualize them and also finding the right uncertainty set. So with this package that is still a big work in progress, we're actually working into formulating optimization problems easily and canonicalize them by removing the uncertainty easily, and then also connecting it with a training procedure that solves this problem in order to train the uncertainty sets. So ideally, in the long term, we would like to have something that looks like this. If we want to formulate a problem that depends on the uncertainty nu, and we have this linear constraint A plus B of U, and then you have these parameters B and A in the uncertainty set, you can formulate it building on top of CVX pi, this problem where U is an uncertain parameter, and then the uncertainty set is an object that depends on your data that are realizations of U. Okay, and then the idea is that we should be able to train it after you formulate the problem, and this will do the job for you by generalizing the class of CVX pi problem. Now, let me show you what happens for this uncertainty set that we showed at the beginning. This training procedure, actually, depending on where you start, actually give you the uncertainty set that we were talking about before. So this is still, if you remember, the portfolio problem that I mentioned at the beginning of this part of the talk. And this value Y is the previous holding. So the lines that you see here are the constraint level curves, which are after you solve the problem for a given theta and a given Y, we fix X and T, and then we draw the line for varying U, which is U1 and U2. And you could see that these are straight lines because it's a linear function of U, and they touch the uncertainty set as they should because this constraint is tight at optimality. So let me show you a slightly more a larger example in 10 dimensions, just to show you what happens for this portfolio problem. Same problem as before, but now it's in larger dimensions. And I compare several approaches. So I have LRO, which is our tuning procedure that reshape a robust optimization problem. Then this is by reshaping our problem, but also fine-tuning the size of the uncertainty set afterwards to exactly match the target probability of constraint violation over training data, which is 0.03. Then I do the same tuning procedure with the mean robust optimization set, which is the one that we saw at the beginning. Same procedure with the tuning afterwards, the mean variant robust optimization problem, and the Wasserstein distributionally robust optimization problem. The first row is the auto-sample average objective. This is the auto-sample probability of constraint violation. Beta is the confidence, and T is the time to solve these problems after training. And these are the Pareto curves that we obtain by changing the size of these uncertainty sets. Okay, so you can see that these trained procedures give you a better trade-off between auto-sample objective and probability of constraint violation. And also the computational time that we need to solve these problems changes depending on the formulation that we have. So the robust problem is a simple, robust ellipsoidal set, so it takes a very short time to solve. The mean robust problem has 3 clusters here, so it takes longer, probably an order of magnitude longer than the robust optimization problem because there are multiple clusters. And the mean variance set takes this similar to the robust optimization problem because it has the same form, just different shape. And the Wasserstein distributionally robust optimization problem takes significantly longer than all of these because you need to take into account all the samples that you need to reformulate this constraint. But the interesting thing is that the Wasserstein DRO problem, of course, has a big improvements over the robust optimization problem, but by just reshaping the set, an ellipsoidal set for this family of instances that you care about, you can do much better just with the robust ellipsoidal set. And now I chose an example with 10 stocks because you could actually visualize what happens. So if you have, these are the average returns for each one of the stocks, and these are the allocations after we vary the target, the auto-sample probability of constraint violation on the x-axis, and these are the weights on each one of the stocks. And you could see that the stocks with higher returns, of course, you don't only pick the ones with higher returns, you need to think about the variance of the stock. If they're very risky stocks, you don't pick them. But interestingly, the reshaped sets have much flatter regions because you very closely, you quickly identify which stock. For example, this orange one has not the highest returns, but pretty high, but then it has a high variance, which means that you can be lucky and get very high returns. And to understand that, the Wasserstein DRO problem gives you a set that allocates this amount to this stock very late when you already violating a lot your constraint. While here, for the robust set, you immediately allocate a lot to the orange stock, which is the one that is the favorite one for this class of problems. We have other examples in the paper, but let me just wrap up and conclude. So we looked at ways to optimize the shape and the size of the uncertainty sets automatically, and by formulating a bi-level optimization problem where we used a CVAR constraint to model the probabilistic guarantees that we want to enforce, the differentiable optimization part to actually understand and build uncertainty sets that are decision focused in the sense that they exploit the structure of the decisions in order to we exploit the structure of decisions to build the uncertainty set. And also we built probabilistic guarantees for auto-sample data, and we obtain improvements over standard robust and distribution robust formulation. So this is the link to the experiments. And actually, this is a working paper that we have on arXiv. We're actually going to probably update it this week. So this is but the link will be the same. So before I conclude, I wanted to actually do a quick advertisement. So we will have a workshop at the end of June in Princeton that is called the Princeton Workshop of Optimization, Learning, and Control. So it will be at the intersection of these 3 areas, and we have a fantastic lineup of speakers from all these 3 areas, from great schools and companies, including IBM and Gurobi. Unfortunately, the poster abstract submission deadline has passed, but the registration will open on May 1st. So I really hope to see you all here in Princeton at the end of June. If you have questions, the email is olc24@princeton.edu, or just reach out to me. So let me just wrap up. So today we saw two different machine learning tools that can help us formulate optimization problems in the presence of uncertainty. And compared to traditional approaches, I think machine learning can really help us building robust optimization formulations as models in a similar way as we do for machine learning predictors, where we train, validate, and deploy them. And I think the right way to go about optimization under uncertainty is to actually tune these sets and build automated procedure to do so. And I think that's where, by taking into account, for example, properties of the solution, closed loop performance, and other characteristics, we can build better formulations that can help us and be also more data savvy and more efficient. Thank you very much, and I'll be happy to answer any questions you may have.
Thank you, Bartolomeo, for the great talk. We still have some time for questions, so feel free to either type in the chat or raise your hand and ask directly. I'll maybe start with a nice bigger one. You know, it's really interesting. Everything was really interesting, but the second part, especially, I think, for the potential you talked about. Beyond this portfolio example, I was wondering, have you tried applying this approach to control problems where you have uncertainty in the constraints?
So actually, so I showed mostly portfolio examples to avoid going into, I guess, to explaining different areas. But yeah, we have examples for example, is more of a news vendor problem that is, I would say you have an inventory with different warehouses, and you want to re-optimize where you what you order for each of these supply chain warehouses. So this is another problem that is closer to control. I think there's actually what I was hoping for in this talk is actually to stimulate connections with people in control where we would like to apply this. So I think we are working on solving problems in power systems with this, where you have this, you can model them as there's several interesting control problems where you model the uncertainty of the wind generation using these sets. In the paper, we primarily have problems in inventory and also portfolio, but the idea is for the next step is to actually extend it to those, because the fact that you solve small convex optimization problems at the inner level, this can scale to actually quite much larger instances than the one that I showed you. And it's an offline procedure that can, I think with the right parameters, can definitely help in control. For example, we have some work on building convex optimization control policies together with folks also there at Stanford. This was way before this, but I can see that this could be immediately connected. So instead of looking at the immediate performance that you obtain out of sample, you could use as a metric in your augmented Lagrangian the closed loop performance after a simulation. And I think that can easily go there.
Yeah, that's a nice thought. I think definitely there are a lot of connections. Another thing I was thinking about was game theoretic settings, or settings in which you are reasoning about the uncertainty of other players. There are a lot of things in the community that, in some sense, I think would fit well with this idea of solving an optimization problem with constraints that are parametric or something else.
Absolutely,
you should definitely look into that.
Absolutely, I also think that there's lots of recent interest from several communities, both in OR and control, where the robust optimization problem is studied as a game, and then this falls exactly into what you're saying, that if this could be the set that we're learning in the second part can have tight connection with the understanding of one player has of the other player's decisions.
Yeah.
So there's strong connection between robust optimization and actually bi-level optimization, robust optimization, and games. I think there's lots of interesting areas that can at the intersection of those. Yeah.
Great. Thank you very much. So any other question for Bartolomeo? Okay. I think Bartolomeo left his email here in case people want to reach out for deeper discussions. And I'm sure you will receive connections from the control community as soon as this video is uploaded. Thank you again, Bartolomeo, for the great talk.
Thank you, Giulia, for the invitation. Thank you all for staying here. Also, there were some questions throughout the talk. I was glad to respond to Subrata. That was quite interesting, and questions were on topic, absolutely.
Thank you. And thank you, everyone, and see you all next week for the next talk. Bye-bye.
Thank you. Bye.